All right, on to part 3 of special relativity. Um, so we're going to call the proper length of something the distance between 2 points measured by an observer who is at rest relative to both of the points. So in this, for instance, in this picture, these clouds are sitting still and you're the observer. The distance between the clouds is their proper distance or proper length, and in this case it's 2.01 kilometers, but we'll get there later. All right, so the muon in this picture, which is going from one cloud to the other, all right, appears to the observer to travel a distance L0, right, the proper length, times the velocity times the time. And if the muon is traveling at 0.95 c for 7.05 microseconds, then that gives us 2.01 kilometers. Now, you may remember from last lecture we talked about the average muon lifetime and its at rest is 1.52 microseconds, but that's just average. Some decay more rapidly, some decay later. That's just there's a distribution of that lifetime around that average. All right, so now we see the muon zip across. It goes 2.01 kilometers. It's going 0.95 c, and for us that takes 7.05 microseconds. What does the muon see? All right. In the muon's rest frame, that 7.05 microseconds gets shortened, right? Remember we had t equals gamma t0. Well, t0 equals t over gamma gives us the muon experiences 2.2 microseconds. So, and it sees the observer going by at 0.95 c. But the observer in that amount of time, right? We've got 2.25 microseconds. We're going 0.95 c. So it sees us go only 0.627 kilometers. We see it go 2.01 kilometers. It sees us go 0.627 kilometers. This is called length contraction, right? Length contraction. So length contraction is that the apparent length of something, right? Apparent length of something is its length, its proper length divided by gamma, right? So in this moving inertial frame, the length gets contracted by the factor 1 over gamma. Now, this leads to another one of those paradoxes that doesn't get resolved until general relativity, which is if I have a car going along and there's a hole, if the car is going fast, the hole appears less wide and perhaps the car will make it over. But to us sitting over here on the side, the car looks shorter because it's moving fast, and so it looks like it's going to go in. This is one of those paradoxes not resolved until general relativity. All right, now how do we add velocities when they're relativistic? So if you remember from last semester when we had velocity, here's an inertial frame, right? Here's an inertial frame. This guy pulling the sled defines the inertial frame that this little girl is sitting in. So he's heading along at 1 meter per second. She tosses the snowball at 1.5 meters per second. The little boy sees the snowball coming at him at 2.5 meters a second, right? And in the bottom picture, again, she's in this inertial frame that's moving at 1 meter per second, and she tosses the snowball backwards at 1.5 meters per second. The boy sees the snowball going away from him at 0.5 meter per second. Pretty straightforward. How do you add velocities from an inertial frame? But when we start talking about relativity, it's not that simple. So if v is the velocity of the frame of reference with respect to an outside observer, and u prime is the velocity of an object within the frame of reference, right? Like the velocity of the snowball the girl is throwing within her frame of reference, and u is the velocity of the object with respect to the outside observer, then the actual relativistic velocities add up like this. The velocity the outside observer sees is the sum of the frame velocity plus the internal velocity, but divided by square root of 1 plus VU prime over C squared. So when VU prime over C squared is very small, right, we get right back to the classical answer. But this factor means that the velocities don't quite add up like you would expect, right? Because 1 plus VU prime over C squared is going to be greater than 1, so the actual addition of velocities is always slightly less than what you're expecting. And that also is a consequence of length contraction, right? All right. So that's it for this segment, and I'll see you in the next one.